Hey guys, it's Miss Neely, and for your homework tonight, I am simply going to ask you to watch this video and take notes on your classwork entitled Sampling Distributions. Since we've fallen pretty far behind because of the snow and other weather conditions, all I need you to do today is just watch the video and take notes. Sampling distributions are at the heart of Inference, which is our last unit of the course. Understanding sampling distributions and the probability that is associated with sampling distributions is critical to understanding inference. So we're just going to learn the basics today. We need to be able to distinguish between a parameter and a statistic. We also need to be able to use sampling distributions of a statistic to evaluate a claim about a parameter. So for example, if I tell you that the average SAT score of students at Southern High School is, I don't know, let's say it's 1430, and I take a sample of students and get their average SAT score, and their average SAT score is actually 1500, I want to know if that difference is significant. I want to know, does that difference indicate that the actual mean is higher than the claim, or is it just due to natural variation that we see from one sample to the other? We also need to be able to distinguish among the distribution of a population and the distribution of a sample, and then also the sampling distribution of a statistic. Sounds like a lot of the same terms, but there are some differences in the types of different distributions that we'll be looking at. We also want to know whether or not a statistic is biased or unbiased, and we also want to measure the variability of the statistic, which we can do with respect to the sample size. All right, so the process of statistical inference, this is the whole nutshell of the course. I mean, the whole purpose of learning about probability and statistics is so that we can make inferences about a population or about some sort of chance process, so that we can draw conclusions about a larger population based on just a sample. But we know, too, that when I'm doing a sample, different random samples are going to yield different statistics. And so we need to be able to describe the distribution of a sampling of a sample statistic, and also in order for us to be able to perform statistical inference. We can think of a statistic as a random variable. Obviously, every time I take a sample mean from a sample, I know that the mean is going to be a little bit different every single time. So it's a variable, and I can think of a statistic as a random variable because it takes on numerical values that describe the outcomes of a random sampling process. So here's our sample. It's from a larger population. I collect data on the sample. As long as it's a representative sample, then I can also make inferences about the population, and that's the whole purpose of this course. But we do need to make a distinction between what we call a parameter and what we call a statistic. As we begin to use sample data to draw conclusions about a wider population, we need to be sure, or we need to be clear about whether the number describes the sample or the population. So for example, if I'm talking about the average SAT score, am I talking about the average SAT score of all the students at Southern High School, or am I just talking about the average SAT score of the sample that I've selected? And so we need to distinguish between the parameter as well as the sample. The parameter, remember, the parameter is basically the number that describes a characteristic in the population. So parameter goes with population. In statistical practice, we often don't know the true parameter. So we gather a sample and we calculate a statistic, which is the numeric or the number that describes the sample data. In practice, we often use the statistic to estimate the unknown parameter. And we've been doing that all along. Okay, so we've got some notation. And for a mean, let's see, we need to be able to distinguish, just in a different color. We need to distinguish between whether or not we're dealing with quantitative data or whether or not we're dealing with categorical data. With all of our categorical data, it's all going to fall in the binomial setting. So if I'm interested in like hair color, for example, since hair color is considered categorical, I'm not interested in is the hair blonde or brown or auburn or black. I only would be interested in like perhaps the number of blondes in a room. And in that case, it could be conveyed as a binomial setting. So all of our categorical data now is going to be in that binomial setting where I'm looking at just a success and everything else is a failure. So even if there's 10 categories, I'm only interested in one, and then everything else would fall into the failure category. So in this course, we're going to be dealing with values that can be averaged, and so we'd be dealing with a mean or we're dealing with a binomial setting and we're dealing with a proportion of success. And so those are the two types of measures that we're going to be calculating from a sample. And it's going to be really important to be able to distinguish between the two, because the distributions that we use for the mean and the proportion are different. And so we need to be able to distinguish between the two. When we're dealing with the mean, and I'm talking about the mean of the population, I use the Greek symbol mu. And so that it's spelled mu, like that. And if I'm dealing with the mean of my sample, remember we deal with x bar. And in most statistics courses, not in AP Stat, but in most statistics courses, the population parameter is described with a Greek symbol, and then the sample statistic is usually denoted with just a regular, alphabet letter. So what you might see in other textbooks when they're talking about a proportion is using pi, not as in 3.14, but as in a variable to represent the population proportion. So you might see this in college. In a college stat course, they might use the population proportion and call it pi. In AP Stat, though, we just call it p. So I'm going to put this in parentheses. That's what you're going to see everywhere else. But in AP Stat, we use the capital, or not the capital letter, we just use the letter P to represent the population proportion. If we're dealing with sample data, then we call that P hat. So all of our sample data has some sort of notation in addition to the letter used to represent it. In other textbooks, though, they actually use the letter P to represent the sample. So I'm just putting that out there so that you recognize that in other textbooks, that the notation is a little bit different. But in the AP Stat course, we use a P and P hat to represent the proportion of the sample. I'm going to have to excuse myself for a second because my dog is starting to chew on my carpet. So hang on one second. Okay, I'm back. My dog might start talking to me, though, so just so you know, it's her. All right, so let's take a look at an example. It says, are attitudes towards shopping changing? Sample surveys, oops, sorry about that. Sample surveys show that fewer people enjoy shopping than in the past. A recent survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed that I like buying new clothes, but shopping is often frustrating and time-consuming. Of the respondents, 1,650, or 66%, said they agreed. Notice that we're talking about 66% here. That is a proportion. It's not an average. It's considered a proportion. And so in terms of our notation, I would be either using a P or a P hat, depending on whether or not it represented the population or the sample. In this case, the population that the poll wants to draw conclusions about is all U.S. residents 18 and over, because it says that it's looking at adults, American adults. So we're looking at U.S. residents that are 18 and over. That's the population that we're trying to describe. The parameter of interest is basically the percent of all of the U.S. residents who would agree to the statement about shopping. And we don't know that true parameter. That's what we're trying to estimate. So that is what I would denote with a P for the population parameter, and it's a proportion. The group of the 2,500 adults who were actually surveyed, that's our sample, and the 66% is our statistic. And again, we would call this P hat is equal to 0.66. P is unknown. That would be our population parameter. All right, so you have 6 examples, and what I'd like you to do in each of those examples is identify the population, identify the sample. Remember, the population and the sample are the people or the objects that we're trying to describe, and then the parameter and the statistic are the measures that we're describing them with. And so remember, I also want you to determine whether or not we're dealing with a mean or a proportion. And oftentimes, a proportion is going to be presented as a percentage or a fraction. You might see the word out of. And there won't be any units associated with a proportion. When you're dealing with a mean, you'll see units associated with it, or you might even see the average, the word average or mean in the sentence as well. But you can usually distinguish between the two because a mean is going to have units associated with it and a proportion will not. So I'd like you to go ahead and press pause and go ahead and identify the population, the parameter, the sample, and the statistic for each one of these examples. Okay, so let's go ahead and take a look, and I'm using my notebook to write on instead of my smartboard, so my handwriting isn't quite as neat as it would be if I were using my smartboard, but I'm going to go ahead and just try to go through these practice problems with you so you can understand the difference between the population and the sample, as well as the parameter and the statistic, and then also whether or not you're using the mean or the proportion. So number one, it says Gallup poll asked a random sample of 515 U.S. adults whether or not they believe in ghosts. Of the respondents, 160 said yes. So the population is going to be all U.S. adults. That's who I'm trying to find information about. The sample would be the 515 U.S. adults that we actually asked. So again, I apologize that my handwriting is horrible. The parameter of interest would be the true proportion of people that believe in ghosts. This is not, I might just have to say it out loud and then you can copy. But the proportion of U.S. adults that believe in ghosts are going to be my parameter, and then the statistic is going to be, and I'm going to call this p-hat since it is a proportion, is going to be the 160 out of 515 who do believe in ghosts. I don't even know if I should bother continuing to write because it's just not looking very good. Okay. And number two, it says the Bureau of Labor Statistics last month interviewed 60,000 members of the U.S. labor force, of whom 7.2% were unemployed. So the population is going to be the entire U.S. labor force. Yeah, I'm giving up on writing. And the population parameter, we actually don't know. We don't know in this statement what the true proportion of unemployed Americans are. And so in this case, the parameter would be the unemployment rate, whatever the true unemployment rate is. The sample in this case is going to be the 60,000 members of the U.S. labor force that we are actually interviewed. And the statistic is going to be, again, this is a proportion, it's not a mean. I'm looking at a p-hat value of 0.072, and that's the unemployment rate of the sample. And number three, it says during the winter months, the temperature outside the Parker's cabin in Colorado can stay well below freezing, which is 32 degrees Fahrenheit, for weeks at a time. To prevent the pipes from freezing, Mrs. Parker sets the thermostat at 50 degrees Fahrenheit. She wants to know how low the temperature actually gets in the cabin, and a digital thermometer records the indoor temperature at 20 randomly chosen times during a given day. The average reading is 42 degrees Fahrenheit. So the population in this case, and actually maybe I'll just type it in, maybe that'll be a little bit easier. The population in this case is going to be all the times, or the temperature, actually it'll be all the times during the day. And the sample in this case is going to be the 20 randomly chosen times. The parameter of interest is going to be the actual mean temperature, and that would be the indoor temperature of the cabin. And the statistic would be the 42 degrees Fahrenheit, which would be the mean of the sample randomly chosen time. And this would be an X bar. So I'm actually going to go ahead and write that in because I don't have a character to do that with. So this is going to be a mean in this case. So X bar is equal to 42 degrees Fahrenheit because that is the mean of my sample. All right, and number four, it says a carload lot of ball bearings has a mean diameter of 2.5003 centimeters. This is within specifications for acceptance of the lot by the purchaser. By chance, an inspector chooses 100 bearings from the lot that have a mean diameter of 2.5009 centimeters. Because this is outside the specified limit, the lot is mistakenly rejected. So the population in this case is going to be the carload lot of ball bearings. And the parameter of interest, we actually know the true mean of 2.5003 centimeters, and that would be the diameter. The sample in this case would be the 100 bearings that were chosen. And the statistic, and in this case, again, it would be an X bar, so I'm going to just write X bar, and that would equal the 2.5009 centimeter diameter of the sample. Okay, and then in number 5, it says a telemarketing firm in LA uses a device that dials residential telephone numbers in that city at random. Of the first 100 numbers dialed, 48% are unlisted. This is not surprising because 52% of all LA residential phones are unlisted. So the population would be, all LA households. Wish I could type a little better. And the parameter of interest would be, and we actually know this, and this again is going to be a proportion. Notice that it's given to you as a percent. So I'm actually going to call that P is equal to 0.52. We actually know the true percentage of phones that are unlisted. The sample is going to be the 100 numbers that are actually dialed. And in this case, we're actually talking about the households. And the statistic in this case, this is going to be my p hat. Again, it's a proportion. And if I'm dealing with a proportion, I'm going to be dealing with a proportion in my sample as well as in the population. That's not going to change. And in this case, my sample proportion is 48% that have unlisted numbers in the sample. And then finally, in number 6, it says a researcher carries out a randomized comparative experiment with young rats to investigate the effects of a toxic compound in food. She feeds the control group a normal diet. The experimental group receives a diet with 2,500 parts per million of the toxic material. After 8 weeks, the mean weight gain is 335 grams for the control group and 289 grams for the experimental group. This problem is a little bit different because we're not taking a sample. Instead, we're dealing with a group of rats that have participated in the experiment. So the population would actually be all rats of this type. We'll assume that it's the same kind of rat. And in this case, since I'm comparing 2 different groups, it's actually going to be the true mean difference in weight. And I guess we can say in weight gain, since that's what we're interested in. And the sample are going to be the rats that are in the experiment. And the statistic is going to be whatever the difference is. And so this is actually going to be a difference in 2 X bars. And we'll talk about the difference in sample means and the difference in population proportions or sample proportions in the next couple of units. But the statistic in this case isn't going to be both numbers. It's actually going to be the difference between them. So I would actually probably just write this, and I'm going to write this underneath since I know it's going to look messy. I might call this X bar 1 minus X bar 2 since I'm dealing with 2 different groups. They're X's, by the way. And so it would be 335 minus 289, which I believe is 46 grams. And that would be my sample statistic. And so my statistic in this case is actually the difference between 2 sample means. And again, we'll talk about those types of situations later on in the unit. But again, notice how my values are given with units. That's an indication that I'm dealing with a mean and not a proportion. Okay, so we've talked already about sampling variability. So if we consider the estimate of the 7.2% unemployment rate obtained by the Bureau of Labor Statistics, or the mean difference in weight gain of the 46 grams for the rats in the experiment above, how can we, use these estimates of p hat or the difference in the 2 X bars based on a sample? How can we use them to estimate the true parameters? In this case, it would be a population proportion and a mean for the population. After all, a different sample of workers or a different group of rats would certainly produce a different estimate. This is basically called sampling variability. And the value of statistics, we know, are going to vary in repeated sampling. Every time I take a sample, every time I do an experiment, my results are going to be a little bit different than they were the last time. And it's not necessarily something that's, it considered random. It's a random phenomenon, and it's known as natural variation. Sampling variability is basically the tendency of a sample statistic computed from a number of random samples drawn from the same population to differ. And this is because each sample consists of different individuals or objects in the population. To make sense of sampling variability, we ask, well, what would happen if we took many samples? And in reality, we don't have that luxury. You get one shot. We usually can only afford to do one experiment. We look at one group of people. We have one opportunity to collect a sample from the population because it's very expensive and time-consuming. So we want to make sure that we do it right. And so that's when we go back to Unit 2 and we think about all of the sampling techniques and good experimental designs. But if I consider, theoretically, what would happen if I just kept taking another sample out of the same population and examining the statistic and plotting it over and over and over again? Well, this is called a sampling distribution. Consider taking a large number of samples from the same population and then calculate either the sample proportion or the sample mean from each of those samples. Make a histogram of these values, and there should be a p-hat in there. I don't know what happened to it. There should be a little p-hat right here. And then examine the distribution displayed of the histogram for overall pattern, center and spread, and then any outliers. And again, this is called a sampling distribution. The sampling distribution of a statistic is the theoretical distribution if I were to look at every single possible sample that I could take of the same size from the same population. So let's say I'm talking about students at Southern and I'm interested in the true SAT score. And let's just pretend that I can't find that number on some computer system. And so I'm going to try to determine the true mean SAT score for students at Southern by taking samples. Well, if I think about a number line, let's say this is my number line. The true mean, let's say, is here. I don't know what it is. But every time I take a sample of, let's say I'm taking a sample of 20 students at Southern. Let's say they're all students that have taken the SAT. And I find their average SAT score. So I might have a sample where the sample mean is below the true mean, whatever the true mean is. I might take a sample where the mean is a little bit higher. Maybe I do get a sample where it's exactly the same. I don't know one sample from the next, but I do know that my sample statistics are going to vary. And what I will find is that I'm going to have just as many sample statistics that are above my mean as I do below my mean. And what I'm going to find is that because with any repeated measurements, with any kind of repeated anything, I'm going to start to see a bell-shaped and symmetric distribution. So it turns out we can actually use a normal curve to describe a lot of sampling distributions. There are certain criteria that have to be met, but in general, the more samples I take or the larger my sample, the more normal my distribution becomes. And then I can just use what I know about normal curves. If I can estimate what the mean and the standard deviation of this distribution is, then I can actually use probabilities to estimate the true proportion or the true mean of my sample, of my population. Let me show you what I mean about sampling distributions. We're going to first look at it for X bar. And I have this little, it's not letting me. Okay, so we're going to first do, all right. So this is a simulation of what it would look like if I were to take a bunch of samples from this population. So this is the population, some population. Notice that it is bell-shaped and symmetric. And basically what I'm going to do is I'm going to start taking samples of size 5, and I'm going to be finding the mean. So as I hit begin, let's see. So those are the 5 individuals that were randomly selected from my population. The mean was calculated and then dropped down to the number line here. If I were to take another sample, notice it's going to be a different 5 individuals. And in that case, notice that the mean was the same as the one before. I can keep doing this. Those are the next 5 people that were selected. Then their mean was a little bit higher. I select another 5 people. There's their mean. I can do this 10,000 times. And that's what my distribution looks like. Notice that in my original population, the mean was right here in the center. If you take a look, now this represents what we call our sampling distribution. I'm looking at different samples of size 5, and I took 10,000 of them. And so by taking 10,000 samples of size 5 from the same population, look where all those means ended up. It still looks bell-shaped and symmetric, and the center of my sampling distribution is exactly the center of my population. Well, let's see what happens if I take samples that are a little bit larger, like let's say samples of size 20, and I'm not going to animate it. I'm just going to this time take 100,000 samples of size 20. That's what my distribution looks like. So notice that the larger my samples, the larger the samples that I drew, notice that the mean is still in the same place. So my sampling distribution is still centered around the same mean as the population, but notice now my spread is a little bit smaller. There's going to be less variation. If I'm just drawing one person at a time out of my population, those values are going to vary a lot. If I start grabbing 5 people and taking an average, the extreme values are going to get absorbed in the average. If I start taking samples of size 20, it's going to absorb those outliers even more. So my sampling distributions, you won't see any outliers. I'm sorry, the clicking that you hear in the background is my dog. So it may make sense to you if you have a normal distribution that the sampling distribution is going to be normal. But let's see what happens if the distribution is skewed. And we can start with 5. And notice that oops, I meant to do this. Samples of size 5. And let's just go ahead and take a quick look at what would happen if I took samples of size 5 and I did this 100,000 times. I just want to point out right here, so this red line right here, I'm sorry, let's see, oh, that blue little line right here is the mean. So that's where the true mean is. So if I take 100,000 samples of size 5, oops, I didn't want it to be animated. 100,000. There we go. Notice that the distribution, if this is where my mean is, notice that the mean of this distribution is very, very close to the mean of the population. Now, even though the population was skewed pretty significantly to the right, notice that my sampling distribution isn't quite skewed as much. And if I were to take samples of size 20 and let's just go ahead and do 100,000 of them, notice that it's not skewed at all. My sampling distribution is now symmetric. It's bell-shaped symmetric, and notice that the standard deviation is much lower. So the mean, notice, is 8.08, and the mean of my population is 8.08. So anytime you're looking at a sampling distribution, the center of your sampling distribution is going to be exactly the same as the center of your population, even if the population is skewed. Okay, so that's if we're dealing with means. We also have simulation for sampling proportions, and you've sort of already seen this in one of the activities that we did with the normal approximation of the binomial. So this is a binomial scenario. It's a simulation where it's talking about coin tosses, but I can change the probability of getting heads, and I can also increase my sample. Instead of tossing it 5 times, again, I can toss it 100 times or whatever. And then I can change the number of repetitions. Let's just look at samples of size 100. If my probability of success is 0.5 and n is 5. Now you should remember back from when we were looking at the binomial distribution, generally speaking, if my probability of success is 0.5, I'm going to have a symmetric distribution. But I can't really call it normal unless n times p and n times 1 minus p are both greater than 10. And in this case, that wouldn't happen. They'd both be 2.5. So if I were to draw 100 samples, you'll see that the distribution is relatively symmetric. What would happen, though, if I was looking at 50 tosses and I did it 100 times? Okay, we can still see that the distribution is bell-shaped and symmetric. And if I were to change the probability of success, like let's say to 0.2, and I think in both cases the n times p and the n times 1 minus p are going to both be greater than 10. And in this case, notice that it's bell-shaped and symmetric. If I were to look at a probability of success of, say, 0.8, bell-shaped and symmetric. And so, in our probability of success out of 50, the average, this isn't I'm not sure how this is looking, but anyway, you can see that when I'm doing a sampling distribution of p hat, it's also going to be bell-shaped and symmetric. And that's really important because we're going to be using a normal approximation for our sampling distributions, at least to get started. All right, so a couple of things that we need to do. When we're talking about any kind of distribution, remember, we always describe the shape, the center, and the spread. So what we've just seen from the simulations, the fact that statistics from random samples have definite sampling distributions allows us to answer the question, how trustworthy is a statistic as an estimator of the population parameter? To get the answer, then we have to consider the center, the spread, and the shape. So let's talk about the shape first. For large samples, the overall shape of the distribution is going to be symmetric and bell-shaped. That's very important. Under certain circumstances, we'll be able to use the normal distribution to model many sampling distributions. There shouldn't be any outliers or other important deviations when we're looking at large samples. In terms of the center of the sampling distribution should be very close to the true parameter, which is either going to be mu or p, whether we're dealing with a mean or a proportion, from the population that the samples are drawn from. And this is because the shape of the sampling distribution is going to be approximately normal. We're going to use the mean to describe the center. So even though we may be dealing with a sample proportion, we're actually going to find the mean of the proportions, which can get kind of confusing. It sounds redundant. And the mean of a sampling distribution is either going to be mu or p. When we're talking about bias, remember back when we're dealing with sampling, when we're actually looking at sampling methods, we talked about bias as being like a systematic favoritism towards one outcome. That's going to affect our sampling distribution. If I've done something to sway responses to a questionnaire, or if I've done something in my sampling method where it's not random and there's bias somewhere, then the center of my sampling distribution isn't going to be centered around the true mean or proportion for the population. And this means that that my sampling distribution would be biased. So bias concerns the center of a sampling distribution. A statistic used to estimate a parameter should be an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being measured. So what we should see, if I've done a good random sample, if I've done a good controlled experiment, is that my sampling distribution is centered around the population mean. If I've introduced any kind of bias, what that means is, it's, like I said, it's a systematic favoritism. So either the center of our sampling distribution is going to be off. And there's really no way for us to know for sure. I mean, if we could figure out what the population parameter was, then I wouldn't need to do any of the statistics. But if there's any kind of bias, it just means that the center of our sampling distribution is going to be off. Spread, again, because we're going to be dealing with a normal distribution for the most part, we're going to be using standard deviation to measure spread. So we're actually going to be looking at the standard deviation of sample proportions, which I know, again, sounds sort of redundant. One of the things you should note is that for larger samples, the variability is going to decrease. And so the variability of a statistic is described by the spread of its sampling distribution. The spread is determined by the sampling design and by the size of the sample. And we know that larger samples are going to give a smaller spread. And as long as the population is much larger than the sample, remember our 10% rule, as long as the population is at least 10 times as large, the spread of the sampling distribution is going to be approximately the same regardless of the population size. So our sampling distribution depends on the size of the sample, not the size of the population. All right. You're given 4 different examples here, and basically you're asked to determine if there's high bias or low bias, and high variability or low variability. So remember, bias deals with center. These are all bullseyes, so imagine throwing the darts at the bullseye. If you're systematically off-center, then you know that you have high bias. If your darts are scattered all around, then you know you have high variability. So I'd like you to go ahead and press pause and describe each of these situations as either having high bias or low bias, and high variability or low variability. Please press pause now. Okay, so in the first one, notice in this case, all of the dots are really close together. That tells us that we have low variability. But they're all off-center, so none of them are hitting the bullseye. That means we have high bias. And number 8, notice how we have the dots are all over the place. That means that we have high variability. However, the dots, even though they're not like right on the center, they are spread evenly around the center. So this tells us that we have low bias. I should say bias, sorry. And number 9, this is like the worst case scenario. The dots are spread all over the place, telling us we have high variability. We also have high bias because we're not on center. So this, again, is the worst case scenario. Number 10 is the best case scenario because we have low variability. All of our results are very close to the center. They're not spread out very much. And since they're all close to the center, we also know that we have low bias. So variability deals with spread, bias deals with the center. And that's really all I need you to know in terms of sampling distributions. We're going to get into more detail about the sampling distribution for the sample proportion and then the sampling distribution for the sample mean in class. So just a couple of things that you need to make sure that you understand is the difference between the parameter and the statistic. Remember, a parameter is the value that describes the population. So just remember they both start with P, population parameter. And the statistic is the value that describes the sample. And they both start with the same letter as well, sample statistic. We're going to use sampling distributions of a statistic, whether it's P hat or X bar, to evaluate the claim about a parameter. And we do that with hypothesis testing. We'll do that in the next couple of weeks. We also need to be able to distinguish between the distribution of the population, which could be skewed or symmetric, doesn't really matter, the distribution of the sample, and then, which is just going to be whatever values you actually see in your sample, and then the sampling distribution of the statistic, which generally, if you have a large sample, should always be bell-shaped and symmetric. We also need to determine whether or not a statistic is an unbiased estimator of the population parameter, and we have to be able to describe the relationship between the sample size and the variability of the statistic. And we'll get into all of that detail as we start looking at sample means and sample proportions. Thank you guys very much. Have a great night.